EMG question of the day. Which of these waveforms is a fibrillation? Please take a look at these figures and choose A or B. Those of you that remember question 19 may ask how come the wave recorded at the end plate is triphasic and not biphasic with negative initiation as we describe being characteristic of end plate potentials. I will explain why in the next few frames. This is a drawing of 3 muscle fibers and 2 neuromuscular junctions. When the axon terminal is about to reach the muscle fiber, it loses its myelin. The terminal button, looking like a vine, burrows into the small mound constituted by the end plate. Notice that in this drawing, one shoot of the axon terminal has been cut and removed, exposing relatively deep grooves under it. These grooves are the synaptic gutter or primary synaptic cleft and the junction of folds or secondary synaptic clefts. Now I like to bring to your attention this region of the terminal button, which I will figuratively transversely cut and use an electron microscope to visualize the elements constituting it as shown here. I will start by pointing to you the presynaptic region of the neuromuscular junction, the junction, and the junction of folds, denting in the end plate. So, were we to place a needle right at the junctional folds, as an action potential is triggered and a symmetrical quadrupole arises under it, we will record a biphasic initially negative potential. But if we insert a new electrode a little to the side while still in the end plate, the activity captured by the needle will not be the symmetrical quadrupole that occurred under the site of acetyl release, but the traveling asymmetrical quadrupole, thus a triphasic wave be recorded. The transition between the recording of a biphasic wave and a triphasic wave following a muscle fiber action potential occurs between 0.4 to 0.6 millimeters from the site of the action potential initiation. So, using the volume conduction theory, symmetrical versus asymmetrical quadrupoles, we can explain the presence of end plate triphasic wave as the consequence of recording needle being introduced at the edge of the end plate. Now that this is decided, let's look at the 3 findings in the figure present in this question that help us distinguish fibrillation potentials from end plate potentials. One is that the intervals between the initial baseline departure and maximal negativity last longer in fibrillation potentials than in end plate potentials. If we draw a broken line delineating the interval between the baseline departure and the negative peak, as you see in this frame, we find that the interval in the end plate potential is about 1/4 briefer than in the fibrillation potential. Why? This diagram represents the linear relation between the distance from the end plate in millimeters and the time to maximal depolarization in milliseconds. The distance from the end plate is measured starting plate folds, which we will refer to as the center of the end plate, to 15 millimeters away. So a potential recorded at the distance of 5 millimeters from the center of the end plate will take about 2 milliseconds to achieve maximal depolarization, whereas a potential recorded 10 millimeters from the center of the end plate will take about 3.5 milliseconds to achieve maximal depolarization. I will show you 2 examples. I have now added a triphasic potential. Notice that the value of the x-axis is 1 millisecond. So, based on this chart, we can see that a potential recorded 0.6 millimeters from the site of its origin has an interval from baseline departure to maximal negativity of 0.8 milliseconds, whereas a potential recorded 5 millimeters from its origin will have an interval of about 2 milliseconds. Notice that here the x-axis value is 2 milliseconds. Now let's look at the second finding that distinguishes fibrillation from triphasic potential present in our examples. This finding is based on the same principle that supported the first finding. The finding is that the interval between initial baseline departure and maximal positivity lasts longer in fibrillation's potential than in end plate potentials. In this frame, I have added interrupted lines demarcating these landmarks. And as you can see, the end plate potential interval is about 1/5 shorter than the fibrillation potential interval. The third finding that distinguishes fibrillation potentials from end plate potentials presented in the figure used in this question is the most obvious. Fibrillation potentials have a flat baseline, whereas end plate potentials have wavy baselines. The wavy lines can be easily appreciated in the 3 superimposed end plate potentials shown here. Also remember that end plate potentials usually fire irregularly. They sound as the cracking of your fingers or sputtering fat in a frying pan. And as we just mentioned, between the potentials, the background activity is wavy, sounding like a seashell. One more thing, a needle in the end plate hurts. So the answer to this question is A. Thank you very much for your attention.